In this video, we're going to look at the connection between definite intervals and geometry. But first, we're going to begin with a warm-up. If you have not completed this warm-up, make sure you stop the video, complete the warm-up, and then resume the video to make sure to check your work and to see if you got them correct and if you have any questions that need to be answered. So the warm-up tells us to evaluate each expression below, identify general solutions and particular solutions. So letter A, we're finding the antiderivative of 4x squared plus 1 over x. So the antiderivative, the first term is going to require the reverse power rule. So we're going to increase the power by 1. So that'll give me 4x cubed over 3. And then the second term, remember, is a good friend of ours. When we find the antiderivative of 1 over x, the function that has a derivative of 1 over x is our good friend ln of the absolute value of x. You have to put that absolute value when you go backwards, so make sure that you do that. And do not forget the plus c, the constant of integration. Letter B. What function has a derivative of sine x? And we know that that is negative cosine x plus the constant of integration. Because we're dealing with trig, make sure that you always check that, because tricky trig. So I think to myself, the derivative of cosine is negative sine times a negative gives me positive sine, so it takes me where I started, so I have that one correct. So the first two are good, and I have plus c. Letter C. This time we have an anti-differentiation problem, and we have an initial condition. We have a given value of x. So first, I'm going to do the antiderivative of the first term. The antiderivative of e to the x is e to the x, our favorite function. The antiderivative of 5 is 5x plus our constant of integration c. And so then we're going to substitute 0 in place of x, 0 in place of x, and we're going to set this thing equal to 3. So 2e to the 0 plus 5 times 0 plus c is equal to 3. E to the 0 is 1 times 2 is 2, and of course 5 times 0 is 0. So we have 2 plus c equal to 3. If I solve for c, I will get c equal to 1. So this one is a particular solution. I need to go back and label my other ones. So my function specifically is 2e to the x plus 5x. The value of c is 1, and so this is a particular solution, meaning that we were able to evaluate the specific family member that we were looking for. So this is a particular solution because it's a particular family member. We were able to evaluate c. The first two items were general solutions because we did not have enough information to evaluate which of the particular family members. We just get a family of functions, so these are general solutions, and we just get to know about the family, not a particular member of the family. In letter D, we are not doing anti-differentiation, we are finding a limit. So when we find limits, remember one of the first strategies is we like to try to direct substitution. So if I substitute 4 into the numerator, that'll give me 2e to the 4 minus 4 minus 2. E to the 4 is e to the 0, and e to the 0 is 1 times 2, and 2 minus 2 is 0. Uh-oh. Looks like L'Hopital may be coming into play here. Then I'm going to have x squared. Whoops, I'm substituting 4. So the limit, let me write this up correctly. The limit as x approaches 4 of 2e to the x minus 4 minus 2 is equal to 0. And let's check out the denominator because I think I'm going towards L'Hopital. So 4 squared is 16 plus 4 minus 20, that's equal to 0. So I can now safely say the limit as x approaches 4 of x squared plus x minus 20 is also equal to 0. So by L'Hopital, I'm going to take the derivative of the numerator, so limit as x approaches 4 of, so e to a power times the derivative of the power, so that's going to be 2e to the x minus 4, and the derivative of 2 is 0, and in the denominator, the derivative of x squared is 2x, and the derivative of x is 1. So I'm going to resubstitute 4 in, and that'll give me 2e to the 4 minus 4 over 2 times 4 plus 1. So e to the 4 minus 4 is e to the 0, which is 1, times 2 is 2. In the denominator, 2 times 4 is 8, plus 1 is 9. So this function is approaching a y value of 2/9, and I do have a graph just to show you. I don't think you're necessarily going to be able to say, oh yeah, that's 2/9. But as x goes to 4, we are approaching a y value of 2/9. All right, L'Hopital practice. All right, go to the blank page 6 in your packet. There is a blank page, and you're simply going to need to take these notes down on page 6. They're not blanks, it's just a blank page, and you're going to write these things down. So let's talk about the two types of integrals. The two types of integrals, the first type of integral is an indefinite integral. So take a look at what an indefinite integral looks like. It has the integral symbol, it has the dx, and it has a function in between. So this is what an indefinite integral looks like. And the operation that is indicated by what you see here is anti-differentiation, which we have just started learning. An indefinite integral provides a general solution, meaning that you have to have a plus c, a constant of integration, or a particular solution when you have enough information provided to solve for c, like we did in one of the problems in the warm-up that we just completed. The indefinite integral gives a family of functions that share the same derivative. So again, this is just reviewing some things that we have recently learned, but just kind of getting it into your head. The indefinite integral is the evaluation of an indefinite integral is a function. So in other words, when you complete this work, when you complete the anti-differentiation, you will have either a general or a particular solution. All right, now moving on to the second type of integral. We've looked at the indefinite integral. Today we're going to focus, or in this lesson, we're going to focus on a definite integral. So first of all, pay attention to how the indefinite integral looks different. The indefinite integral has a lower bound and an upper bound. So that's really the major difference right there, but it is a major difference. It's going to produce a definite integral versus an indefinite integral. And as you will see in our lesson, this is going to reveal an area problem, and you'll see shortly how an indefinite integral is an area problem. A definite integral is the accumulation of area from A, so you're going to start at A, that's where you're going to start your accumulation, and you're going to stop the accumulation at B. So A and B are values of x. Now with an indefinite integral, we said you're going to get either a general or a particular solution. The evaluation of the definite integral is definitely going to be a value, specific value, or a number, because we said, and that makes sense, if the definite integral is an area problem. When you calculate area, you don't get a formula, you don't get a function, you get a specific value, you get a specific number. So those are the two different types of integrals that we will be dealing with. And we've already dealt with indefinite integrals. Now we're going to look at the definite integral. Some things we know from our past. We learned early on in this course that the derivative of position, so s of t, recall, is the position function, is velocity. And the derivative of velocity is acceleration. These are things that we've done in our past. But now we're going to reverse the process and think to ourselves, okay, if we go backwards, if we find the antiderivative or undo or anti-differentiate velocity, that's going to have to take us backwards, back to the position function. And if we anti-differentiate or undo acceleration, it's going to take us back to the velocity function. Okay, let's get into an example that shows us how definite integral is area under a curve. So our big idea, and this is in your packet on page 7, if you're in my class, the definite integral represents net area under a curve. So make sure you write that down if it's not down. Just trying to find my packet here to see what your page looks like. Yeah, so definitely add that in, that the definite integral represents net area under a curve. All right, let's look at our example. As you drive on the highway, you accelerate to 100 feet per second to pass a truck. After you've passed, you slow down to a more moderate 60 feet per second. The diagram shows the graph of your velocity v of t, so we're looking at a velocity graph. As a function of the number of seconds t since you started slowing. All right, so this is time in seconds. So by looking at the graph, what does your velocity seem to be between 30 and 40 seconds? So here's 30 right here. And here's 50 right here. So from 30 to 50 seconds, it seems like our velocity is staying at 60 feet per second. 60 feet per second. How far do you travel in that time period? Well, we're traveling from 30 to 50. We're traveling for 20 minutes. And we're traveling for 60 feet per second. And this takes us back to middle school. We know that distance is equal to rate times time. So if I take my rate of 60 feet per second and I multiply by, that was 20 seconds, not 20 minutes. And I multiply by 20, I get 1,200 feet traveled. All right, so that's how you calculate the distance traveled from 30 to 50 seconds. Now let's think about the geometric representation of the distance traveled over the time period from problem number 2. Over here on the right hand side I have a rectangle, and it's going to be pretty cool. I'm going to slide it right over here. And notice how that rectangle seems to perfectly fit that region under the curve. And so if we were to find, if I had redone this problem and instead of talking about it from a calculus point of view, and I just put that rectangle in there and I said find the area of that rectangle, we would say, well, the span, or the base of the rectangle is 20. So from here to here is 20. And the height of the rectangle is 60, and 60 times 20 gives you 1,200 feet. So there is your first example of seeing how area under a curve, accumulated area under a curve, is a definite integral. We started with velocity. We actually did integration, although you didn't necessarily know it. We did integration and we went back to the position function. So the geometric representation of the distance traveled over the time period from number 2 is the area under V of t from 30 to 50 seconds. In this case, it happens to be a perfect rectangle, but not all of our figures will always have beautiful, nice shaped polygon regions. Consider the accumulation of area under the velocity curve gives us the change in position. So in other words, when we did the anti-differentiation there, it gave me the change in position of the car during that time period. Write a definite integral to represent the change in the position of the car. So let's think about what we just accomplished here. We did calculus, but we did it kind of in a backhanded way. We accumulated the area starting at 30 seconds, stopping at 50 seconds. We accumulated the area underneath of the velocity curve that was given to us with respect to time. And when we did, we got 1,200 feet. Now think about that. Again, what we did geometrically, we're going to learn how to do with calculus. We had the 20-second time period. I want you to see the units multiplied by the 60 feet per second. So there go the units right there. The units are going to divide out when we find the antiderivative. And it's going to, we're going to, basically, when you integrate a rate, you lose the rate, is basically what you can think of. We had feet per second, but those per seconds are going to divide out in the numerator and denominator and give me the 1,200 feet, which takes me back to position. All right, so that's your first experience with a definite integral. So in general, the definite integral from a to b of f of x dx represents the net. That's an important word right there, the net. Notice we didn't say total. In this case, it was total. We'll talk about why it was total versus net. Well, I'll go ahead and tell you. If you look at the graph, all of the area is above the x-axis. We don't have any area below the x-axis. That's where we can run into some problems. So in general, the definite integral from a to b of f of x dx represents the net accumulation of area bound by, so the area, the enclosure, the region that holds the area or sets the area up for us is x equal to a. So we start at the lower bound of a. We stop at the upper bound of b. The x-axis is one of the bounding curves. It could be the ceiling, it could be the floor. And the function, the curve itself, is another boundary of the region that we're going to find the area. Since the definite integral accumulates the net area, if there is any area, very important right here to pay attention to, if there's any area bound below the x-axis, the accumulation is negative. So kind of think about that for just a second. Area below the x-axis is counted negatively. Area above the x-axis is counted positively when it comes to the net accumulation. Below the x-axis, negative. Above the x-axis, positive. Very important. All right, so let's use what you've learned to determine the distance you travel from 0 to 20 seconds. So notice we're going to have a little different region here. So here is 20 right here and 0 right here. Now let's go ahead and write our definite integral of what we are finding here. We're going to accumulate the area starting at a lower bound of 0, so start at 0, stopping at an upper bound of 20, and we're still accumulating area under the velocity curve. And we know that that's going to give us change in position. In this case, it's actually going to give us distance traveled, because in this problem, all of the area is positive. So this is going to give us feet. Now, we just learned that a definite integral is a net accumulation of area. So the way that we're going to determine how far we have traveled is right now, we're going to use an estimation strategy. So notice right here, we have perfect, beautiful rectangle from here to here. So that's going to give me 5, 10, 50. So that's going to give me 20 by 60. So this piece right here is the 1200 that I found earlier when I was at a different part of the curve. So I've got to figure out the area of this region up here. Now the way we're going to do that is we're going to count the blocks. So that's going to be, notice that these blocks are not all whole blocks, so we're going to kind of have to piece them together, and this is where the estimation strategy comes from. So I'm going to, and very important to put dots in so that you don't overcount something. So this would be 1, and this one is close enough to me to be counted as a whole block, so I'm going to say that's 2. This one is close enough as well. I'm going to say that that's 3. I say that this one and this one together make 4. And then this little piece, this little piece, and this little piece maybe make a half. So I'm going to say that that was 4.5 blocks. Now, it's really important when I count blocks. So remember, so far I had 1,200 feet that I was able to account for. These blocks, be careful, these are not 1 by 1 blocks. So 4.5 blocks is not 4.5 blocks. It's 4.5 multiplied by, so 1 block, come down here, this is 5 by 10, 20, 30, 40, 50, 60. So that's 5 by 10. Let me make sure I counted that right. So 5, 10, 20, 30, 40, 50, 60. So 5 by 10. So it's 4.5 blocks, but 1 block is equal to 50 feet of area. So when I multiply 4.5 times 50, I get 225. This is an approximation. And so when I combine 1,200 plus 225, I get 1,425 feet as the approximate distance traveled from 0 to 20 seconds. Number 7, what must you remember when you are using the counting block method to determine the area? Well, when you're using the counting block method, you have to determine the amount of area in 1 block. The temptation is going to be to think that you're always dealing with 1 by 1s, but in most cases you actually are not dealing with 1 by 1s, so be careful with block counting. And nice, we've already completed number 8. We've already written our integral. We've already found the distance traveled by the car. So let's see what this looks like in practice. So notice when we look at some of the example problems, the first example that I've given you has some area that is above the x-axis and below the x-axis. So let's just kind of take a minute to look at that. So this region right here, this area that is enclosed between the curve, the x-axis, and in this case 0 and 2, that is positive area. In this region, this area is negative area because it is below the x-axis. And then everything back over here after 6 to how far we go, that is all positive area. So positive, the blue counts as positive, the red counts as negative. All right, so in this case, we have a velocity function, another velocity function, and x represents time, and we are going to find the total, now be careful with these words, we're going to find the total distance traveled. No, but a definite integral accumulates net area, but this question is demanding that we find the total distance traveled. So we have to express the distance traveled as a definite integral. All right, so let's take a look. During the first 2 seconds, well, as we've already talked about, during the first 2 seconds, the area that is enclosed is above the x-axis, so that's going to be all positive. So we're not worried about getting the total distance traveled because we're only moving in one direction. So the total distance traveled would be the area accumulated from 0 to 2 underneath of f of x dx. And I actually can do this by counting blocks, but in this case, that looks very triangular-ish. In other words, this region right here, I think is close enough to a triangle to just do 1/2 base times height. So I'm going to do 1/2 of the base, which is 2, times the height, which is 2. So 1/2 of 4 is 2. My units, remember, since I had feet per second times seconds, so feet per second times seconds, I'm going to end up with feet. So that is the total distance traveled by the object from 0 to 2 seconds. Now, the first 6 seconds, we have to be really, really careful. So we're going to take the area of the total distance traveled that we already found, which was 0 to 2 of f of x dx. Remember, that was positive area. That was all good. Everybody's happy about that. But now the next region from 2 to 6, that has to be calculated as negative. Now, if I subtract, think about it. If I subtract, as I'm supposed to, because this is going to give me net area, then I'm not going to get the total distance traveled. I really want to ignore that I'm changing directions. So instead of adding the next definite integral, I'm actually going to subtract. So I'm going to subtract the integral from 0. Whoops, not 0. We're starting at 2. So 2 to 6 of f of x dx. All right, so I'm going to go back over here. I'm going to get rid of my colorings because now it's time to count blocks. So I'm going to count. That's 1 whole block. That's 2. And this one together with this one, I'm going to say is 3. And this is about, I would say these two together make about 1/2. All right, so remember from part A, we already had 2 feet traveled. Now we're going to subtract what we just found. So I had 3.5. I have to, and in this case, the blocks are 1 by 1s. So we're going to subtract negative 3.5. Now, why is this negative? Because a definite integral accumulates net area. The net area in that region is negative. That's why I had to subtract the negative to force all of the area to be positive. So the total distance traveled is 5.5 feet. And this all kind of goes back together with your velocity curve being positive and negative and traveling to the right, traveling to the left. So it's kind of all coming back together here. All right, and then for the last one, we're going to do for the first 8 seconds. So we are going to accumulate starting from, we already had 0 to 2, that was positive area, all was good, dx, and then we had to subtract the negative area from 2 to 6 of f of x dx, and now the area switches back to positive, so we can add the area from 6 to 8 f of x dx. So the first region we had traveled 2 feet, and then for the next region we had minus negative 3.5, and now we're going to go back for 6 to 8. So to me looks like another triangle, so 6 to 8, 1/2 base times height, so that's 2. How tall is that? To 7, 2 times 7 is 14, half of 14 is 7. So that's 2 plus 3.5 plus 7, which is 12.5 feet. All right, so hopefully this is making sense. Net accumulation of area, and that the area that is below the x-axis is negative, so I have to switch the sign to force it to be positive, because in that region the object is traveling to the left. All right, letter G is your first example of, or the next example is your example of nonsense units, to make sure you understand what's happening when you integrate the rate. So if g of x represents a velocity function, and this is the graph of g of x, and x represents time, find the total distance traveled. Again, an override. It doesn't want net area, but we're going to use net area to get the total distance traveled. Express the distance as a definite integral. Give correct units. Now notice that the time is measured in bloops and the velocity is measured in bleeps per bloop. I would encourage you to stop the video, to do these yourself, and to go back and see if you get it. And that way you'll have a good idea of whether you're tracking with this or not. All right, so we want to find the distance traveled during the first bloop. So we're going to accumulate the area starting at 0, stopping at 1, but I notice that that region is negative, so I'm going to negate that to force the area to be positive. Under g of x dx. Again, that region looks to me to be triangular enough to say half base times height, so that's going to be the opposite of negative half of 1 times 1. This negative is here because we are accumulating area below the x-axis. This negative is going to negate that so that I get distance traveled versus simply just change in position. So that'll give me 1/2. Now let's think about the units. We have bleeps per bloop multiplied by bloops. So the bloops divide out, and that gives me 1/2 of a bleep. Very important that you understand the unit analysis and that you're able to come up with the units regardless of how nonsense they are. All right, now we're going to go during the first 4.5 bloops. So 4.5, all right, so we're going to start with what we did before. We're going to negate the region from 0 to 1. That was negative area. Beginning with 1, the graph goes positive. Whoops, let's finish writing that up before I change colors. So g of x dx. All right, now the area goes positive, so we're going to add. We're going to start at 1, and we're going to stop at 4.5. All of that area is positive, so that's good to go. G of x dx. We already knew that the area for the first region is 1/2 of a bleep. And now we're going to count some blocks here. So 1, 2, this one, and this one I'm going to say is 3. This one and this one I'm going to say is 4. And maybe 4.75, 4 point, nah, it's actually a little, I'll say 4.75 just to make it easy. So that's 4.75. And these are 1 by 1s, so we're good to go. So plus 4.75, which gives me 5.25 bleeps. And then lastly, the first 5 bloops. So we're going to do the same thing. We had 5.25 was the distance we had traveled so far. The area at 4.5 is going to go negative again. So we're going to force that area to be positive by subtracting, negating the negative region. So we're going to negate the area accumulated, starting at 4.5, stopping at 5, under g of x dx, which gives me 5.25 minus, and I'm going to say that that little region of area is about 0.25, so minus negative 0.25. So that's actually going to make us add that in, so about 5.5 bleeps. All right, so this is your first experience with area under a curve. So hope this helps.